Okay, so elevator questions are a very, very common type of Newton's second law question. Okay, they're mathematically very straightforward because all the forces involved are collinear. The forces are up and down. Okay, what force would be down? Gravity. Okay, and the force up is usually identified as tension. Okay, because usually there's a cable that's pulling up on the elevator, and any pulling force we call tension generally. Okay, so those would be the two forces that would be acting on an elevator. All right. The other day we talked about how to calculate the force of gravity. Okay, we said that Fg equaled m times g, where g was the acceleration due to gravity, which most of the time is going to be 9.81 meters per second squared. Okay. M is the mass of the elevator, or occupant in kilograms, and then Fg is the force of gravity, or sometimes also weight. Okay. Now, when you are in an elevator, does your feeling of weight change? You ever had that sensation when the elevator first starts to descend that you suddenly feel a little bit lighter, your stomach kind of goes up into your throat? Okay. Well, that's because, not because you are lighter, okay, or that your weight has changed, but something we call your apparent weight has changed. Under most conditions, your actual weight and your apparent weight are the same. Okay? Because your apparent weight is how much weight you feel. You don't actually feel your own weight. Okay? You only feel your own weight when there's a responding force to it. So that force for you right now is the force of your chair. Okay? Your weight is sitting on the chair, and the chair is pushing back. Okay? So you don't feel that as, well, you feel it as your weight, but it's actually your apparent weight. Your real weight is a downward force. What you feel is the chair pushing back. Now, when you're in an elevator, that apparent weight changes. Because in order to either accelerate you up or down, the elevator has to push on your feet. Okay? If the elevator is going to descend, that is, accelerate downwards, then the force of gravity needs to be bigger than the force in the elevator. And so you feel a little bit lighter. If you're going to get accelerated upwards, the floor has to push on your feet harder than gravity. So you feel a little bit heavier. You get that sensation of the floor pushing hard on your feet, and your knees bend for a second, and then up you go. Okay? So whenever a question is dealing with an elevator, it's going to use the words weight and apparent weight quite often. Okay? So we need to understand that apparent weight is going to be the upward force. Okay? And it's going to equal the tension and things like that. Okay? And then your actual weight is the force of gravity, and it's acting down, and it's always your mass times 9.81. Okay? Now, if you're falling, do you feel weightless? You do. Okay? While you're falling, you feel weightless. You feel weightless because there's nothing pushing back on you. You still have weight, that's why you're falling. Okay? But because there's no upward force from any other object, you don't feel that weight. Okay? And there's lots of situations that we'll actually talk about in Unit 3 where we can produce a feeling of apparent weightlessness. You're not actually weightless, but you feel weightless because of your motion. Okay? Does everyone understand the difference between real weight and apparent weight? Okay, so in this example here, and I'll have you write it down because it's a good initial elevator example. Okay, person and an elevator have a combined mass of 600 kilograms. Okay, the elevator cable exerts a force of 6,500 newtons up on the elevator. Find the acceleration of the person. Okay, so they've already got a free body diagram there, but it's so big it doesn't fit on the page, so I'm just going to redraw it. Okay, so there's our elevator, 600 kilograms, and they've told us that the elevator cable, okay, so the force of tension, that's supposed to be a capital T, okay, equals 6,500 newtons. Is that the only force acting on the elevator? What other force is acting on gravity? you'd be surprised how often people forget that. Okay? Not usually with an elevator, but if I say I throw a ball straight up in the air and I use X many newtons to throw it, oh, suddenly gravity's out the door. People forget it. Okay? They don't realize that if I throw something up in the air, that's an elevator. Okay? If it's straight up, it's an elevator. The force of my hand pushing and the force of gravity pulling are in opposition to each other, and I'm elevating whatever it is I'm throwing. Okay? But as soon as I change the context from an elevator to throwing something, people just forget. Okay? So gravity is there, and can I calculate it?
You already have it.
Well, I have the acceleration due to gravity, but I don't have the force of gravity yet. Right? That's m times g. So I have the 600, the mass, okay? And I know that g is 9.81 because I have to assume this elevator is on Earth.
I was just gonna ask, wouldn't you already have the force of gravity considering the fact it's going up and down and gravity was just pulling straight down? I mean, why would you have to calculate it?
Because I won't be able to get the net force if I don't have the number.
Oh,
Does that make sense?
okay.
Yeah. Okay. So I've got mass 600, okay, times 9.81. That's going to give me 5,886, yeah? Yeah, newtons. Okay, so the force of gravity is 5,886 newtons, and the force upwards is 6,500 newtons. So the force upwards is bigger. Which way is the elevator going? Up. At a constant velocity or accelerating? Accelerating. Force is bigger up than down. Is there an unbalanced or net force here? Okay, if there's a net force, then the object's going to accelerate. Okay, so they want the acceleration of the elevator slash person. They're going to go at the same rate because when you're in an elevator, you and the elevator accelerate at the same rate. Okay, so if I'm going to calculate acceleration, I'm going to need net force. Since I don't have acceleration, I can't calculate that with m times a. But I could calculate it using the other way to calculate it, which is?
Would you subtract the force going up by going down?
Exactly, the vector sum of all forces. Okay, I would subtract the force of gravity from the upward force. Okay, or add them and make that negative, whichever. Okay, so I don't know what that was supposed to be. 6,500, okay, minus 5,886 should give me 614 newtons, yeah? Okay. All right, so I've got 614 newtons as my net force. Now, I can do this, okay, because I have F net and I have mass. Okay, so now I can calculate the acceleration. So 614 divided by 600 is going to be 1.0 something. Okay, 1.02, I think, we have 3 sig digs, right? Yeah, we do. Okay, so 1.02 meters per second squared up. Okay, because my net force is also up. Okay? So we actually did some questions harder than that yesterday. Okay? Elevator questions are pretty straightforward, but the wording of them can get tricky. Okay, and I think I've said this a few times already, but that's the real challenge with Newton's second law, is being able to read and interpret a question and get exactly what's going on from it. Okay, but generally, elevator questions, anything accelerating up or down, straight up or down, is an elevator. Okay, and they can be considered to be solved this way. Okay, now sometimes an elevator question will give you a weird situation. Let me grab some. not. Our bathroom scale is gone. Another bathroom scale in there. This is a weird situation. It seems to come up often in elevator questions. There's a person in an elevator standing on a bathroom scale. Why? I don't know. But that's the context of the question. Now, what the bathroom scale reads, if I'm just standing on it in the elevator and the elevator is not moving, is my what? My weight, right? Well, actually, it reads our mass, but it uses our weight to do it. Okay, again, that's that North American problem that we have. Okay, so we're going to say it's a bathroom scale that actually shows newtons. I stand on it, it tells me how much I weigh. Is that bathroom scale going to read different numbers if I'm accelerating up and down? Yes. Because the bathroom scale will tell me how hard the floor is pushing on my feet. Because that's the force that bathroom scales use. Okay? When you step on a bathroom scale, okay, so you step onto it, okay, it says, get off, get off! What? Yours doesn't say that? Okay, so you step on the scale and it reads, what you do is you compress a spring. Okay, so the scale isn't actually reading the force of gravity pulling down, it's reading how hard the spring is pushing up. Okay, those forces are equal, and so that's why we can use it that way. But they're only equal if the floor isn't moving. Once the floor starts to move, then the scale might push harder or less on you. Okay, so if the elevator suddenly descends, is the bathroom scale going to read a bigger number or a smaller number? Smaller, because it's going to fall away from me, right? It's not going to push as hard, and I'm going to, oh, I love that number, while I accelerate downwards. Okay, and then when it comes to a stop, and then starts to go back up, I'm going to cry. Probably already crying anyway, but okay, it's going to push harder on my feet, and it's going to read a bigger number, because in order to accelerate me upwards, the floor has to push on my feet harder than gravity would normally push. Okay, so I'm just kind of giving you all the situations you might get with an elevator. Sometimes they'll say it's tension in the cable, and other times they'll weirdly say that someone is standing on a bathroom scale in an elevator, because that's a thing. Okay, at least in physics, not obviously in the real world. But you could try it if you were ever really curious. Okay, and that's exactly what would happen. Okay. All right. So if we had the bathroom scale, we could just go to the elevator and we could try it. All right, questions on how that works? All right, I want you guys to try these two elevator questions. Okay, so we got person in the last example, so that's the 600 kilogram elevator. Okay, so the mass is still 600 kilograms here, just so you have that. Okay, now the elevator cable only exerts a force of 5,200 newtons. Okay, find the acceleration of the person. And then we'll talk about number 2 because it's a special kind of elevator question. So for now, actually just try question number 1. Okay, so as I said, I mean, the thing with elevators is as long as you remember that gravity is present, you really can't go wrong. They're not difficult. The forces are collinear and opposite. So we have our 600 kilogram elevator. Okay, we have an upward force of 5,200 newtons, and gravity is still the value we calculated before, 5,886 newtons. All right, so now the force of gravity is greater than the upward pulling force of the cable. So which way is the elevator going to go? Down. Okay, so we got to calculate our net force if we want to calculate that acceleration. So that'll be the force of gravity minus the force of the cable, so the vector sum of all forces, okay, and that'll give us 686 newtons. Right? Now that we have that, now we can calculate the acceleration of the elevator, so 686 newtons divided by the 600 kilogram mass of the elevator, okay, and that's going to give us 1.14 meters per second squared down. Okay. Now, here's another trick. Sorry, are there any questions on that? There's no trick on that one. Ty, question?
I put the numbers backwards, so I did 5,200 minus 5,886.
So you got negative 686?
Yeah,
Yeah, and that's okay. Then you would have got negative 1.14,
yeah.
right? And you just have to recognize that that means down.
Okay.
I just made down positive in this,
Okay,
but you could do it that way too. As long as you don't write negative down, because negative down is
down, or up.
up, yeah.
So if I put my answer on the test as negative 1.14, that'd be good?
No, that wouldn't be good. Question gave you up and down.
Oh, okay.
Okay, so our vector has to match what the question gives us. Now, mathematically, like you'd get like 4 out of 5, because mathematically the answer is correct. Vector speaking, it's not. Okay,
Would the weight of the person also add to the weight of the elevator?
yes, but it's considered. In the first question, it said the mass of an elevator and its occupant is 600. So yeah, absolutely. If they don't say that that's the mass together, I would have to put the mass of the occupant in as well. Yeah. Okay, that's good. You guys are starting to read into these. Like you're noticing those kinds of things that are important details, right? Okay. Tricks that can happen with a question like this. Instead of asking you to calculate the acceleration, I might give you the acceleration of the elevator instead, and then ask you to calculate the tension in the cable. How would that change the question? Would it change any of the steps?
Maybe instead of using A equals F over M, you'd be using F equals M times A.
Right, yeah. I'm actually gonna use the same steps, but I'm gonna do them in a different order, okay? Instead of doing M times A last, I'm gonna do M times A first, okay? Because in a situation like that, so if I just like quickly make one up here. Okay, so let's say I've got this elevator, and it's the 600 kilograms, okay? But instead of giving you this number, the tension, I tell you that the acceleration is 1.3 meters per second squared up. And then I say calculate the tension. Okay, so now I have the mass and the acceleration. Okay, what can I calculate with mass and acceleration? Net force, okay? Which the last time we did this question, we used the vector sum of all forces to get, but we can't do that now. We don't have all the forces. We're being asked to find one of them instead. Okay, so what I would do there is say, okay, I'm gonna calculate F net by going M times A. So I'm gonna go 600 times 1.3, and that will get me my net force. Okay, so 780 newtons. Up. Okay, because I said the acceleration is up. Everybody okay with that so far? Okay, so this number here is my net force, which is also the vector sum of all the forces acting on the elevator. Okay, so now what I have to do is go, all right, this 780, which is my F net, can also be calculated by going force of gravity plus the tension. Okay? Now, can I calculate the force of gravity right now? I can. I've got the mass. If I have the mass and I know what G is, it's 9.1, I can calculate that number. This is the number the question wants me to calculate. So I'm going to subtract Fg over to the other side. So I'll have 780 minus Fg equals the tension in the cable. All right, now, here's where vectors come in though. That 780 is up, and it's positive. Gravity needs to be negative. Okay, so I'm going to have 780 minus negative 5,886 equals the tension. So when I subtract the negative, I'm actually doing what? Adding. Okay, now, does that make sense? That's going to make a number bigger than 5,886. That's good, right? I need a number bigger than gravity, otherwise the elevator is not going to be accelerating upwards. Okay, I need that net force. Basically, I'm just adding that net force onto the force I already had. That'll give me the other force. Okay, so that's gonna be,
6666.
oh, wow, really?
Yep.
That was really bad luck.
Yeah.
All 4 sixes?
Yep.
Okay, well, it's 4 sixes. That's okay. That's okay. All right. Newton's up. Okay, so we haven't done one like that, but I mentioned that sometimes a Newton's second law question will give you acceleration and ask you to calculate one of the forces. Elevator questions are a very common example of that. Okay, now that's actually not the trick. That's just another way that the question can be asked. Here's the trick. What if instead of saying the acceleration of the elevator is 1.3 meters per second squared up, I say find the tension in the cable when the elevator is moving up at 1.5 meters per second. Did I give you an acceleration or a velocity? Okay, if the elevator is moving at a constant velocity, what's the net force? Right. The net force is 0 because the object's not accelerating. M times A, right? There's no acceleration, so the net force has to be 0. So in that case then, if it's still this elevator, what's the tension in the cable? Keeping in mind that we just said the net force is 0.
Equal to gravity.
Equal to gravity. Right? The force up and the force down would have to cancel each other or add up to 0. Okay, does everyone follow me there? Okay, so and that's a very common elevator question trick. Okay, is to say, here the elevator is, calculate the tension when the elevator's acceleration is this, when the elevator's acceleration is this, and when the elevator's velocity is this. And people just they get in the habit of doing things with acceleration and they forget constant velocity means no net force. Okay, that is a common trick actually in all kinds of questions, where they'll say the object is moving at a constant velocity of this many meters per second. People plug it in as an acceleration when they shouldn't. Okay?
If you're looking for weight though, how do you figure out what the force net going down is? Because you times mass by gravity to figure out the tension of the thing going down. If you don't have the mass, then what would you do?
That's this question.
Yeah.
Okay, so let's have a look at question number 2. Okay, so question number 2 is what we call a differential acceleration question. Okay, that makes it sound really complex, much easier than the name would imply. Okay, so I have this electric chain hoist that's lifting an engine out of a car. Okay, engines are really heavy. And you usually need some sort of leverage or electric motor or something like that to lift them. Okay, so what I've got is this engine that it's attached to that I don't know the mass of. Okay, but I know that the chain hoist can exert a force of 2,850 newtons. Okay, and I know that the engine is accelerating at 1.5 meters per second squared. So my net acceleration is 1.5 meters per second squared. Okay, now what's the other force acting on the engine? Gravity. And as Ty was pointing out, I don't have any way to calculate that right now because I don't know the mass. What do I do know about it?
It has a constant velocity.
Gravity?
Or no, sorry.
Gravity but it has a known what?
Acceleration.
Acceleration. I know the value of the acceleration due to gravity. So I can just say G, or AG if I wanted to, okay, is 9.81 meters per second squared, and I'm going to make it negative because that one's up. All right. So if this is true, the force of the hoist plus the force of gravity equals the net force. That's true, right? That's the vector sum of all forces. Problem? I don't have any of those forces, and I don't have the mass. Well, sorry, I have the force of the hoist. Okay? I can't calculate the force of gravity because I don't have the mass. I can't calculate the net force because I don't have the mass. But here's the thing. This is m times a. Okay? A net. This force of the hoist is mass times the acceleration of the hoist. And this is m times g. What do they all have in common?
M is in every single one.
M is in every single one. What can I do with m?
Cross it out.
I can cross it out. Now, people really get antsy about that because what's the question asked?
For the map.
What's the mass? And I'm canceling it. Don't worry, I'm gonna get back to it. Okay, so the relationship between net force is the same as for net acceleration. That's why we call it the differential acceleration method. I can use the difference in the accelerations the same way I could use the difference in the forces to get my net acceleration. And I know what the net acceleration is. They told me. And I know the acceleration due to gravity. So I know 2 out of the 3 accelerations. Everyone okay with that idea? Okay, so can I calculate the acceleration the hoist could produce? I can. Okay, so I'm just going to bring gravity over here, and I'm going to have the net acceleration minus the acceleration due to gravity equal the acceleration of the hoist. Okay, so then I'm going to go 1.5 minus negative 9.81.
1.5 is the net.
Is the net, yeah, is the net acceleration. So it's the acceleration being produced by the net force. Okay? All right, so I'm getting 11.31 meters per second squared. So each force can individually be calculated by going mass times the acceleration that force would produce. That's why m times g calculates gravity. That's why m times a net calculates net force. Okay? Any force can be calculated by multiplying mass by the acceleration that force would produce by itself. Well, I know the force that the hoist can produce. The question told me what it was. They told me it was 2,850 newtons. And just a minute ago, I canceled that out right here. Okay? So can I calculate now the mass? I know the force of the hoist. I know the acceleration the hoist can produce. I can calculate the mass. It's the only thing that's missing. Okay? So the force of the hoist equals mass times the acceleration of the hoist. Okay? So now I just bring the acceleration over here, okay? And I calculate the mass. So 2,850 divided by 11.14, okay? And I get 252 kilograms, which is like 600 pounds or so. Okay? Now, I have never, ever put a differential acceleration method question on a quiz or a test. I show them as an example, and then I say, see? Good. And then I go on to other things. Okay? As long as you understand, all I'm trying to illustrate here is that forces and accelerations work the same way. I add their vector sum is going to be the net. Okay, so net force is the vector sum of all the forces. Acceleration is the vector sum of all accelerations. Average velocity is the vector sum of all the velocities together. It all works for all vector quantities. Okay, and that's all we did there. Okay, so 252 kilograms, almost 600 pounds. Anyone see the original Fast and Furious movie? No, sorry, not the original. Fast and Furious. Was that 4 or 5? Anyway, they get ridiculous. But, okay. In one of the scenes, Vin Diesel grabs a chain hoist with an engine on the end with one hand and holds it from falling on a person while interrogating him. Realistic? I mean, dude's big. You know, he's strong. He's got big arms, but nobody's holding a 600-pound engine, even with the aid of pulleys, with one hand. while interrogating someone perfectly calmly like they're not even exerting themselves. Now, had it been The Rock, maybe. Apparently they don't get along. That's what it is. Like they can't even be in the same room, apparently.
Who would win that?
Wasn't it a draw the one time they had one in the movie? I don't know, it's gotten so ridiculous when I watch it anymore. Okay, so that's a differential acceleration question. Let's get that one. Okay, I would like you guys to try question number 1 about the bungee jumper. We got time for that? Yeah, we do. Okay. Is bungee jumping an elevator?
Yes.
Yes, because it's vertical. Okay. Okay, so let's quickly look at this one here. So we've got our 55 kilogram bungee jumper. Okay, and thankfully they fasten one end of the cord to the bridge. That's a key part of bungee jumping. Otherwise it's bungee falling. Okay. Then she jumps off the bridge. As the cord is stretching, it exerts an elastic force directed up on her. Calculate her acceleration at the instant the cord exerts an elastic force of 825 newtons up. Okay, what force am I missing from my free body diagram? Force due to gravity. Yeah. Okay, can I calculate that right now?
No.
Yes, can. I got M and G, right? I mean, we're assuming this is happening on Earth where G is 9.81 and they tell us her mass is 55 kilograms. So we can do that. So 55 times 9.81. Okay, and so that's 539.55. Okay. Is there more force up than down? Which way is she accelerating? Which way is she moving? Downwards. Yeah. Okay. I mean, she could be moving downwards. She could actually be moving not at all. This could be the very bottom of the thing where she stopped for an instant. Okay. That direction of movement doesn't have really anything to do with the direction of the acceleration. The bungee cord is slowing her down. It's doing what it's supposed to do. Her acceleration can be up and her velocity can still be down. That's okay. Right? Okay, so we calculate our F net. Okay, vector sum of all forces, so 825 plus negative 539.55. Okay, will give us our net force. Okay, so 825 minus that number. Okay, so there's our net force. We divide that by her mass. Okay, she's accelerating upwards at 5.2 meters per second squared. We only have 2 sig gigs there. All right, is that making some sense? Okay, so on Monday, we're going to start getting into some more involved examples. Okay.